It's a pleasure to introduce Rustam Sadykov from Kansas State University, who will talk about the Lusternik-Schnirelman theory of four manifolds.
Right. Hello, everyone, and thank you very much for inviting me to give a talk here at the seminar. So I will start my talk with just a general review of covers and fillings. So let M be a smooth closed manifold, then a cover of M is a collection of open subsets of M such that M is covered by these open sets. And there are quite a few covers that are interesting to consider. We can cover manifolds by sets that are contractible. We can cover manifold by contractible sets. We can cover manifold M by just balls. These different things lead to different notions. Like, for example, cut M plus 1 is the minimal number of sets contractible in M. G-cut M plus 1 is the minimal number of contractible sets in M in a cover. And there is also a notion B-cut M that corresponds to balls. So these are covers. And I will also consider fillings. These were introduced first by Takens in the case of three-dimensional manifolds. And then this notion was extended for high-dimensional manifolds by Zinhoff. So a filling of a manifold M is a collection of compact codimension 0 smooth submanifolds with corners, such that you basically take the manifold M and you cut into these smooth pieces with corners, so that the interiors of your pieces are disjoint. So there is a somewhat complicated condition over here, but for me, I will just, maybe I have to make it a little bit bigger, I think. So, but I will just say we also require that adjacency of these compact manifolds QIs should be nice. So what we basically, in the neighborhood of any point which is in the boundary of several of these sets, the sets should look like half space, like in this example, or quarter space, and so on. So basically, in the neighborhood of any point which is in the boundary of several of the compact manifolds, the compact manifolds should look like sectors, coordinate sectors. So all adjacencies are very good. So we take a manifold, cut them into pieces, and whatever we cut, we basically cut along some coordinate planes. So examples of fillings, interesting examples of fillings include fillings by topological balls. I will denote the minimal number of topological balls needed for filling by B cut M plus 1. So B is capital here. We can cover manifolds by contractible manifolds, and we can also cover manifolds by smooth balls. Of course, here, when you consider fillings, in most of the cases, you consider manifolds with corners, because otherwise, say, for example, if you have three, if you cut your manifold into three pieces, then it's already almost impossible to avoid corners. And also, when I say that I'm considering fillings by topological balls, what I mean is that I consider actually filling by smooth manifolds. All fillings are smooth. But these manifolds in the filling, they should be homeomorphic to balls. So there is a distinction between topological balls and smooth balls, because in general, there might be exotic balls. We don't know if they exist, but there might be exotic balls, and they may exist only in dimensions 4 and 5. And these are manifolds, smooth manifolds, that are homeomorphic but not diffeomorphic to balls. So Zinhoff and Takens considered simplifications of fillings, and so I will not state the general theorem by Zinhoff. Let me just say that in the case of dimension 4, which is of interest to me, I will be skipping in this talk some of the theorems that I prepared, basically because I realized at the end that there is no way for me to cover everything I prepared. So I apologize for having this on the notes. Unfortunately, it's not as easy with written notes to remove what you prepared as with electronic document. But in any case, in the case of dimension 4, the Takens-Zinhoff theorem gives us the following statement, that every simply connected closed four-dimensional manifold admits a categorical filling by one handle bodies. And here categorical means that you are cutting your manifold into the same number of pieces as you need to categorically cover the manifold. So if you have, for example, a simply closed form manifold, we will see that the category is 3 in this case, unless this is a sphere. This means that by the Zinhoff-Takens theorem, every simply connected closed form manifold admits a filling by 3 one-handle bodies. In fact, fillings by one-handle bodies are quite important, and I will discuss them later. These include examples of Heegard decompositions of 3 manifolds. So you take a 3-dimensional manifold and split into one-handle bodies. And in 4-dimensional case, we have trisections, which were not so long ago discovered by Gay and Kirby. So here also, basically, in Heegard decomposition, you can encode Heegard decomposition by a surface with 2 families of curves. So every 3-dimensional manifold can be encoded by a surface with 2 families of curves, and every 4-dimensional manifold can be encoded by a surface with 3 families of curves. So trisections are basically the same as Heegard decompositions, but for 4 manifolds. And these are examples of interesting fillings. So I will have 3 parts in the talk. So in the first part, I will be discussing a category of M, and over there are 2 theorems. One theorem is by Aprea and another by myself and Dranishnikov. But actually, our theorem follows from the first theorem, and these are not actually theorems; these are basically observations. That in one case, that the category of manifold M is less than or equal to 2 if the manifold is orientable, and pi1 is free. And in our so we have a different argument using connected sum formula, the same statement, but where pi1 is 0. And I will discuss both theorems, both approaches. Then I will be discussing B cut of M. So this is the fillings of a manifold M by topological balls. And in this case, actually, the manifold M is not necessarily 4-dimensional. It could be of arbitrary dimension. And we proved that in this case, there is this that 1 plus B cat M is bounded from above by the minimal number of critical points of functions without infinitely degenerate critical points. And this should be compared with the theorem of Carnère, who estimated, also considered functions without infinitely degenerate critical points, so to say, reasonable functions. And in this case, there is an estimate in terms of cone length of default M. So with Stanislav, so this is joint work with Stanislav Trunov, and with Stanislav Trunov, we also proved the upper bound for cret.m. So here we need to consider covers by smooth balls. So over here we consider covers by topological balls, and here we consider covers by smooth balls. In dimensions except for 4 and 5, this is the same as this. And so in this case, we have a precise value for cret.m. So this is just 1 plus b cat m. And this is nice because this can be, so b cat m. So this is a filling by balls, and this can be easily compared with category with all other invariants that we consider. And finally, I will be discussing covers of the manifold M by smooth balls. It's a case where M is four-dimensional and simply connected. And in this case, with Stanislav Trunov, we proved that B cut of the manifold M, so it's less than or equal to 3 in this case. And basically the question is, when is it 2? And the answer is that B cut M is 2 if and only if M admits a handle decomposition with no handles of indices 1 and 3. This actually, the proof of this theorem is somewhat interesting to me because it involves trisections. We, in order to prove this theorem with Stanislav, we introduced the notion of a homology trisection. So we studied with him homology Heegard splittings and homology trisections, and we proved that a homology trisection implies the existence of a trisection by balls, and this implies the theorem. So I have 3 parts of the talk, so I will start with categories, the category of the manifold. So suppose that the manifold M is an oriented closed form manifold with a free fundamental group. Then Aprea and Strom observed that in this case, the category of M is at most 2. And this is how the argument goes. So if we start with the manifold M, whose fundamental group is free, if we remove a disk from that manifold, then what remains is homotopy equivalent to a wedge of spheres. And the category of the wedge of spheres is 1. So together with the disk we removed, we get that the category of M is at most 2. If you look at this argument by Aprea and Strom, so you can see that basically you can suspect that maybe in this case where the manifold M has free fundamental group, maybe B cut of M is also at most 2. And so if you apply the same argument, then you suppose that there exists an inclusion of this wedge of spheres, which is a homotopy equivalence. Then you take a tubular neighborhood of this embedded wedge of spheres. And if you take this tubular neighborhood, then you can see that the tubular neighborhood consists of basically a disk and handles, such that each I handle corresponds to the I-dimensional sphere in the wedge. And then, of course, the B cut of this is just 2. Is it 2? It's 1. So B cut plus 1 is 2, right? So this is basically the same argument as in the argument of Aprea and Strom. And then you can suppose that when you add the additional disk, right, then you just get a decomposition. But here there is a problem, and this problem is very complicated. Is that you can, in general, we don't know that such an embedding exists. So there is such a map which induces a homotopy equivalence, but we don't know if this can be made into so that there is an embedding that is a homotopy equivalence. Even if the manifold is, say, for example, simply connected, in this case, the spheres are of dimension 2. So you map a wedge of 2-dimensional spheres into 4-dimensional manifold, and those 2-dimensional spheres are going to intersect. And so this is a very hard problem. So this is almost a dead end. So in this direction, if we go in this direction, it's really hard. There might be another approach to this, and this is by means of the connected sum. We don't have such a strong theorem with Alexander Dranishnikov as in the statement of the theorem by Aprea Strom, but we used a different approach, which uses connected sum formula. The connected sum formula states that the category of the connected sum of M and N is the maximal of categories of M and N for any closed connected manifolds. We actually proved the theorem for orientable manifolds a few years ago, but for non-orientable case, actually, we couldn't prove at that time the theorem, and we just recently proved it. And this turned out dependent on Ivase manifolds. So basically, one has to study Ivase manifolds, because when you take connected sum of the manifolds, what you do is you're removing a disk from M, you're removing a disk from N, and then you are gluing them together. And when you remove a disk, then usually the category drops. But for some manifolds, the category does not drop when you remove a disk. And because of that, these cases, they should be treated separately. And so basically, we just investigated Ivase manifolds and we deduced this theorem. Now, if one knows the connected sum formula, then the category of a simply connected four manifold can be computed very easily, because we know that if you take a simply connected four manifold and then you take the connected sum with CP2 and CP2 bars, then you get a connected sum of CP2s and CP2 bars. So now, by the connected sum formula, the category of the left-hand side is the maximum of the category of M and the maximum of the categories of CP2s. But the category of CP2s is just 2. So the left-hand side is the maximum of the category of M and 2. And as for the right-hand side, so this the category is 2, the category is 2, the connected sum has category 2, and so the category of M is 2. So basically, if one knows the connected sum formulas, then one can prove this. Now, so in order to calculate B-cut, one basically asks, is it true that there is this connected sum formula? So if one can show that there is this connected sum formula, then just by the above, by the argument in this corollary, one can calculate B-cut for simply connected four manifolds. But we don't know if this is true or not. And I also would like to mention the following, this conjecture. So this several people apparently worked on this conjecture, including Alexander Drinishnikov and Yuliy Rudyak. And in fact, I learned about this conjecture from Alexander Drinishnikov. And so this conjecture states that the minimal number of critical points of functions on the connected sum of two manifolds, M and N, is the maximum of cret M and cret N. So this is a connected sum formula for critical points on of functions on manifolds, and it's not known. So now, so let me go to the second part of the talk. Let me just kind of go back to this. So this is like my plan, right? So let me now discuss the second part of the talk. And as I said, this very much should be compared with Carnér approach. So let me review the theorem by Carnér. So the Lusternik-Schnirelmann theorem says that the category of M plus 1 is less than or equal to the minimal number of critical points on the manifold M. But it's actually advantageous to, there is an advantage to consider not the category of M, but the cone length of the manifold instead. So the definition of a cone length is that you construct the space X by attaching cones. So you start with a point, and then you have a sequence of maps such that every time xi plus 1 is obtained from xi by attaching a cone. So that this is a cofibration, to be precise. And then if you need n iterations like this to get space X, then the least number n is called the cone length. And the fact is that the cone length is very close to the category of X. So if it differs from category of X, then it differs just by at most 1. So Carnér proved that there is this Lusternik-Schnirelmann type inequality in the case where F has only reasonable critical points. So reasonable critical points means critical points that are not too degenerate. And I will say a little bit more in a second about this. So one may wonder about inequality in the other direction. And the inequality in the other direction, it's true, but only in some cases. So to formulate the inequality, to have the inequality in the other direction, one needs to assume that everything is simply connected. And every time, so if you have this cone length decomposition, then in every cone length decomposition, the base of the cone, it should be of fairly small dimension. It should be half the dimension, roughly speaking, should be half the dimension of the manifold W on which you consider the function. And so if you can construct this W starting from a point and then attaching cones of small dimension, then in this case, the converse to the Lusternik-Schnirelman inequality also holds. So the basic two will be just the same. And I also promised to say what does it mean that a critical point is reasonable. So it basically means the following. So if you have a function on a manifold, then every regular fiber of the function is just a manifold. But a singular fiber is not a manifold. It has a singularity, just one singularity. And so the statement that a point X is reasonable is means that the pair of a point and the complement of the point gives a Whitney stratification of the singular fiber. So I will not talk about Whitney stratifications, but this is some notion about how different strata in stratifications are adjacent, and this is this is a necessary condition over here. We have a slightly different notion. Maybe these two notions are the same. I'm not sure, but we kind of came up with a different notion of non-degeneracy. So to define this, assume that M is a smooth manifold, and suppose that sigma is a submanifold with one critical point. So sigma is a subset such that you remove one point from the subset and you get a submanifold. So here's the picture, right? So U is so it's a neighborhood is a manifold M. So sigma is a subset in the manifold M, and if you remove X from sigma, then you get a submanifold. Suppose that there is a neighborhood of this singular point, and suppose that there is a function f on this set U, and such that this function has two properties. That outside of this point, the function has no critical points. So this is the only critical point of this function. And also, when you restrict f to sigma without x, remember that sigma without x is also a manifold, because sigma is a manifold with just one singularity. So if you remove this point x, then sigma is a manifold. And so the condition is that f restricted to this sigma also has no critical points. So in this case, you can see that the picture is basically a cone. So this sigma, it approaches x as in the cone. So this part of the sigma in U is a cone. And because of that, we say that x is a cone-like singular point of sigma. So the reason why we want this definition, the reason why we want to consider this cone-like singularities, first of all, let me actually define what does it mean that a critical point of a smooth map is a cone-like. So a critical point of a smooth map is cone-like if x is a cone-like singular point of the critical level of the point x. So suppose that x is a critical point, you just look at the critical level, and suppose that x is a cone-like singularity of this critical level. Then we say that x is a cone-like critical point of the function f. So the reason why we like this definition is because we can prove that the set of germs of non-cone-like critical points is of codimension infinity in the space of germs of functions. So these non-cone-like singular points, they almost never appear. So, and in singularity theory, they are basically ignored completely. But here for this problem, I'm not sure that we can ignore them. But in any case, so let me show how to prove that. So let me show that this non-like critical points are of infinite codimension. So the argument is entirely a singularity theory argument. So one considers the so-called jet space. So this is the space of Taylor polynomials on the manifold M. And then in singularity theory, there is a notion of finite singularity type. So basically, singularity theory only works with finite singularity types jets. So if you take the jets that are non-finite singularity types, they form a subset of codimension infinity. So this is known. And then it is also known that if you have a map germ, which is a finite singularity type, then this map germ is so-called K-equivalent to polynomial. And K-equivalence is a major equivalence relation singularity theory. But then if F is K-equivalent to, for polynomials, it's very well known that critical points of polynomials are cone-like. And then one can show that if two map germs are K-equivalent and one of these map germs has a cone-like critical point, then the other function also has a cone-like critical point. And so basically this argument shows that that we consider all singularities, that singularities theory studies. And so it means that indeed the set of non-cone-like singularities is of codimension infinity, right? So say if you have any parametric family, finite parametric family of functions, and this family is generic, then all singularities are cone-like. Actually, I forgot. Yeah, okay, so this is not all. Right. So we denote by crit.m the minimal number of critical points of functions with only cone-like critical points. And we expect that crit m is the same as crit.m. So we considered many cases, and really it's very hard to construct something that is that would not satisfy this. So we think that crit m should be the same as crit.m.
Rustam,
yes.
Would you remind me what the superscript D means on the BCAT?
Right. So here, so if you don't have D's, it means that you're covering the manifold M by balls, but these are topological balls. So these are smooth manifolds that could be very complicated, but homeomorphic to balls. Over here, we consider covering of the manifold M by balls, but that are really diffeomorphic to balls. Yep.
And when you're covering by the balls, you don't make their interior, you don't have to make their interiors disjoint, you just need to cover it by balls?
No, you actually consider a filling. So this is what was this definition of a filling. So when we we just cut. So I said covering, but yeah, you're right. I should have said that I'm consider filling. So I'm cutting the manifold into pieces, and the pieces should be the interiors of pieces should be disjoint, and they should be adjacent as coordinate sectors are adjacent. So this is the filling, and so the minimal number is called B. This B cat D. Right?
Okay.
So this is Thank you for the question. So I should have reminded it. Right. So this is filling by smooth balls. This is fillings by topological balls, and so. And as I said, this B cat M and B cat DM, they are the same, except possibly in dimensions 4 and 5. So in dimensions 4 and 5, these are open questions, but otherwise these two are the same. So next, I wanted to discuss this example of just. So this may be I wanted to discuss an application just to show that this statement is non-trivial and show how this statement can give a non-trivial conclusion. So let's consider a so-called Mazur manifold. So how to construct a Mazur manifold? So you start with S1 cross D3, right? And to S1 cross D3, you attach a thickened disk, right? So this is a two-handle. Two-handle means that you are attaching a two-disk and then you thicken it, right? So how do you attach this D2 cross D2 to S1 cross D3? So you attach it as handles are attached along the boundary. So the boundary of S1 cross D3 is S1 cross S2. And in this S2, you can look, for example, at the upper hemisphere. This will be a disk. So the boundary of this, so the boundary of S1 cross D3 contains S1 cross the upper hemisphere. So S1 cross D2. And this is a solid torus, so I just have drawn this solid torus over here. And now I need to attach D2. So as I said, basically up to homotopy, so what you're doing, you're just taking S1 cross D3 and you're attaching D2, and then you're just thickening this D2. And so when you attach D2, you just need to look at the boundary of this D2, right? And so the boundary of D2, it should be the same as on the picture. And so in this case, so you get a manifold, which is actually not diffeomorphic to a disk. This will be a complicated manifold, but it's actually homotopy equivalent to a point. It's contractible. And it's easy to see why it's contractible, because you see, so over here, up to homotopy, you were just attaching D2, and then this is up to homotopy is just S1, and so you're just attaching D2 to S1 as a boundary, and the attaching map here, you can see that this is of degree 1. So it's, of course, what you get is something contractible. And in fact, you can actually argue even better. So you can take this attaching sphere, and if you modify the attaching sphere by homotopy, you do not change the homotopy type of the manifold M. And of course, you can modify this by homotopy, the circle, into the central circle of the solid torus. And so if you do so, then you get just a ball. And so it means that M is homotopy equivalent to a ball. But of course, when you have a crossing of the attaching sphere, you don't have a manifold anymore. So it's you're not modifying them by isotopy. You are just modifying the manifold somehow, preserving its homotopy type. And so this is a Mauser manifold. It's a compact, contractible, smooth 4 manifold, which is not diffeomorphic to a 4-ball. And then the question is, so here's the problem, is there a function on this manifold M, on the Mauser manifold, with less than or equal to 2 critical points? Okay, so such that on the boundary F is constant. So this kind of, here I constructed a decomposition of the manifold M into 3 handles. So because over here I have 0 handle and 1 handle, and here's 2 handle. So I basically constructed a function on this manifold with 3 critical points. And the question is, can you construct a function with 2 critical points? So you can see that actually here, if you try to apply any theory, so if you try to do any homotopy construction like Conley index, or if you try to use Hopf invariant or anything, this is indistinguishable from the case of a 4-dimensional ball. Because as I said, you can just by homotopy, so if you can consider a homotopy construction, then you basically are allowing to modify this attaching sphere by homotopy. And of course, you can unlink this. And as soon as you unlink this, you can see that you just have the meridional, so not the meridional, but the central circle of the solid torus. So any homotopy invariance would tell you that this manifold is the same as a disk. And so basically, if you try to answer this problem using category Conley index or whatever, it tells you that you just need 1 critical point. Because, for example, this is contractible, so it means that the Lusternik-Schnirelmann category of this manifold is 0. So there is really, these invariants do not work. But on the other hand, so we can calculate bcat M, and we can calculate bcat D M, and both, so bcat M plus 1 and bcat D M plus 1, these are 3. And so it means that though all these abstractions tell us that probably you can fuse here critical points together, we know that you cannot fuse. So here kind of homotopy abstractions do not tell sufficiently much, do not give us sufficiently much information. And this is one of the reasons why this 4-dimensional case is interesting. So now I'm going to turn to the last part. The last part about this fillings of the manifold M by smooth 3-dimensional balls. And as I said, this will be closely related to Heegard decompositions and trisections. So let me recall that a one handle body is a compact oriented manifold obtained from a disk by attaching one handles. So basically you take a ball and attach one handles in an orientable way, and you get a one handle body. But we are also interested in homology one handle bodies. So a homology one handle body means that we have again a compact oriented manifold. It should have the homology type of the one handle body. So its homology should be the same as homology of the wedge of spheres, because one handle body, the homology of one handle body is the wedge of spheres, is the homology of wedge of spheres. So here we also require that the homology are the same. And also additionally, we require that the boundary is connected. So a homology one handle body is a compact oriented manifold with connected boundary such that it's homologically the same as one handle body. And now we have Heegard decompositions and homology Heegard decompositions, or splittings. So a filling of a three manifold is a Heegard splitting if x1 and x2 are one handle bodies. So this is just standard definition of Heegard decomposition. So we take a manifold and split it, decompose it into the union of two one handle bodies. And we have a filling that is homology Heegard splitting if x1 and x2 are homology one handle bodies. So basically, we just require that the homology of x1 and x2 are the same as the homology of one handle bodies, but this could be more complicated manifolds. And the point is that later I will show that if you have this filling by three smooth balls, then you will get a homology Heegard splitting, and then the point would be to modify the homology Heegard splitting into a Heegard splitting. So let me tell you how a homology Heegard splitting can be modified into a Heegard splitting. So suppose that we have a manifold M, and suppose that we have a splitting of M into two compact submanifolds. Maybe we have a homology splitting into two submanifolds. Then we can have a Morse function such that basically x1 is mapped from -1 to 0, and x2 is mapped from 0 to 1, right? And we can assume that this level is regular. So this is how we can get such a Morse function. We may also assume that we have only one critical point of index 0. We have only one critical point of index 3. So all other critical points are of index 1 and 2. Now I would like to encode this everything in terms of f. So how to encode everything in terms of f? So first of all, how to encode x1 in terms of f? So here f is this black surface. It's two-dimensional. So on this picture, I've drawn this as one-dimensional, but this surface is actually two-dimensional. And then to obtain x1, we just use the Morse theory. So we know that in order to obtain x1, we first need to thicken f, multiply f by 0, 1, then attach one handles, and then attach two handles, and then we are done. So for example, when you attach one handle, this alpha 1, then so here's what you do. So you attach one handle over here. So when you need to attach a two handle, well, you attach it along some attaching sphere. So this is the attaching sphere. So basically you just like attach a disk along this circle. This will be attaching a two handle. And then you need to attach a three ball at the end. And this gives you x1. And the construction of x2 is similar. So you need to attach one handles, two handles. So this is what you're doing. You attach here one handle, you attach here two handles. And so this is kind of generalized Heegard diagram, because you can see that the surface F is just this surface, this black surface, and these dashed handles are attached handles that are not present in F, but they are present in X1 and X2. And now suppose that I want to use this decomposition of the manifold M, and suppose that I want to build a Heegard decomposition, a decomposition into one handle bodies. So what do I need? Well, I need to flip handles. So I need to take all handles of index 1 from the top and bring them down. So all these red handles should go down, and all the blue handles, they should go up. And from more theory, we know that we can modify this, we can do this by homotopy of the function f. So this is called handled rearrangement. Handles of low indices can always be brought down. And so after we take all the red handles down and all the blue handles up, after the rearrangement, we get something like this. Now, if you look carefully, what happens to the index of the handle? So here, if you have a handle of index 1, right, then so here it's basically this handle is attached along a 0 sphere. Then after you bring this handle up, now this handle is attached along a one-dimensional circle. So it means that when you do this operation of rearrangement of handles, in terms of the surface F, the index of the handle is changed. So you can see that now this alpha 1 becomes a 2 handle. So over here, alpha 1 was a 1 handle. But now in this picture, this handle is actually present in the surface. So some surface F prime. So let me say that this is like F prime. This surface is F prime. And now this handle now is present in F prime. And alpha 1 now a one-dimensional circle. So it now corresponds to attaching a 2 handle. So the flip, it brings a handle from X1 to X2 or brings a handle from X2 to X1, and it also changes the index of the handle. So this is how it looks like. Actually, this is, I feel that this description is somewhat oversimplified, and because of that, let me give you an example. So a very nice example of a homology Heegard decomposition, and let us make it into a homology decomposition in Heegard decomposition. So what I do here is I choose some knot. So here's the trefoil, but you can choose your favorite knot in sphere S3. Take a tubular neighborhood of the knot, and denote by X1. The complement, the closure of the complement will be denoted by X. And you can see that the complement of the knot is not necessarily a one-handle body, but homologically it is a one-handle body. The homology are the same as the homology of one-handle body. And so we have a splitting of S3 into two homology one-handle bodies, a tubular neighborhood of a knot and its complement. And now I'm going to show how to turn this into a very nice Heegard decomposition, because this is not a Heegard decomposition, this is only a homology Heegard decomposition. Now we are going to turn this into a Heegard decomposition. So first of all, if you look at the complement, you may realize that the complement has a nice handle decomposition with one handles alpha 1, alpha 2, alpha 3. So these are one handles. It's a little bit harder here to see 4 2 handles, but there are also 4 2 handles, and there is a 3-dimensional ball. So this is the decomposition of the complement. And now, following our strategy, we need to flip one handles from X2 to X1. And so I take these handles and I flip them. So I just cut them out from X2 and I attach them to X1, right? So I attach them to X1. And so now I have a different decomposition of the sphere. So now I want to kind of to draw this picture a little bit better. You can imagine that you just, I'll take it a little bit higher. So you can imagine that you're taking this tube, and you're pushing it over here. right, between these two strands. So you're taking this tube and pushing them between these two strands, and then you make the cylinder into a round form. And if you do so, if you take a cylinder, push it over here, and make it round, then you get instead of a cylinder, you get something like a sphere. And so you do the same with the other two handles, and so you get these three spheres, and the other tubes, they just look like this. So now it's a better picture. One has to be somewhat careful with the attaching spheres in the decomposition of X1. So they, after these modifications, they become somewhat more complicated. And after you do, but in any case, it's actually, when you have such a picture, the decomposition of the complement, for example, is very easy now to see. You can see that you can decompose the complement to the figure into these two handles and a ball. So it means that already have that this manifold is a one handle body, and its complement is already a one handle body. So this is what we wanted. But actually, in our proof, we also need to make sure that this is a standard Heegard decomposition of the sphere, and to make it a standard decomposition of a sphere, we need to use handle slides. So you can take this attaching sphere, and you can slide it along other handles one by one, and by handle slides you can get such a picture. So this picture and this picture, they are related by handle slides. So handle slides are manipulations of decompositions. So we decompose the manifold into handles, and we can modify them in standard way and get such a handle decomposition. So this is a standard Heegard diagram of a sphere. Now, so this was a discussion of three-dimensional manifolds, which is very important for us. But we actually need homology trisections. So homology trisections are very similar to Heegard decompositions of three manifolds, but homology trisections and trisections are for four manifolds. So here's the definition. So a trisection, or respectively homology trisection, is a decomposition of a manifold into three one-handle bodies, right? So again, we take a manifold M, dimension 4, and split it, cut it into three one-handle bodies. In the case of trisections, we require that the intersections are one-handle bodies. In the case of homology trisection, we require that the intersections are homology one-handle bodies. So here's the picture. So here's the dimensional manifold. And we split this four-dimensional manifold into three parts, X1, X2, X3. The common part of these three pieces is a surface denoted by F. And now the intersection of X1 and X2 is denoted by X12. The intersection of X1 and X3 is denoted by X13. In the case of trisection, we require that this X13 and X12 are one-handle bodies. So this is a Heegard decomposition of the boundary of X1. But in the case of homology trisections that we introduced with Stanislav Trunov, we assume that X12 and X13 are homology one-handle bodies, so that this is a homology Heegard decomposition of the boundary of X1. A nice theorem, a very useful theorem, a very strong theorem, is a theorem by Gay and Kirby, which states that every manifold M admits a trisection which is unique up to stabilization. And in fact, this trisection, so it could be very hard to imagine, but it can be constructed in a very nice way. So this is how one can construct a trisection. Remember that when I was constructing a Heegard decomposition, we were just taking a three-dimensional manifold and we were considering a Morse function on that three manifold. Here, the idea is the same, but now instead of considering a Morse function, we consider a map to R2. So you take a four-dimensional manifold, you map it to R2, and then using singularity theory, such a map can be simplified in such a way that it has one component of singular points of more singularities of index 0. So the blue components are singular curves of index 1, and these cusps, these are so-called birthday singularities. And that's it. And you can choose such a map, modify a map by homotopy in such a way that these curves are precisely as in the picture, with no self-crossings or whatever. So this is a very nice picture. And in particular, you can observe that this is symmetry by the group S3, or by Z3, right? So this suggests that we can cut R2 into 3 equal parts, and one can show that the inverse images of these 3 parts are going to be diffeomorphic one-handle bodies, and these are precisely X1, X2, and X3. So this gives a trisection of the manifold M. So this is a fantastic theorem because you know, 4-dimensional manifolds are extremely complicated, but you just can look at the surface F and draw 3 families of curves and completely encode this trisection. So this is a very strong theorem. So the theorem is due to Gay-Kirby, but this construction is due to Baikur and Saeki. So these are recent constructions, so these are new theorems. In any case, now, how do we use these trajections and Heegard decompositions? Well, so here's a theorem, or maybe just an observation, that suppose that M is a simply connected closed 4-dimensional manifold. And suppose that we decompose this manifold M, we cut this manifold into 3 smooth balls. Then this decomposition into 3 smooth balls is actually a homology trisection of M. So this is just some calculations of homologies that one can see that this is true. But this is not, in general, this is not a trisection. This is just a homology trisection, meaning that yes, we are indeed cutting the manifold M into one-handle bodies because balls are one-handle bodies of genus 0. So we are cutting into one-handle bodies, but the intersections right now are homology one-handle bodies. And we want these intersections to be one-handle bodies. So how to do this? So we have seen that any homology any homology Heegard decomposition can be modified into a genuine Heegard decomposition by using flips. So we want to realize these flips in terms of 4-dimensional manifolds. And it turns out that this is possible. We can't realize these flips. And the argument for realization of flips is as follows. So suppose you have this manifold M, 4-dimensional manifold M, and the 4-dimensional manifold M is decomposed, is cut into 3 pieces, X1, X2, and X3. So we cut them into 3 pieces. Here's our surface F. Drawn here is 1-dimensional, but it's actually 2-dimensional. And to define one surgery, we choose a curve in the intersection of X2 and X3. So the intersection is X to 3. We choose a curve over there, which goes from a point in F to a point in F. And now what we do here is we take a tube here in the neighborhood of gamma. This tube is completely in X2 and X3. We remove this tube from X2 and X3, and we attach this tube, this solid tube, to X1. So this is one surgery. And of course, it modifies the decomposition of the manifold M. So now the decomposition is different. But an observation is that the manifolds X2 and X3 are not modified much because we just modify them near their boundaries. So they are basically the same. Boundaries are basically the same, but the Heegard decomposition of their boundaries are now different. And what happens to Heegard decompositions of their boundaries is that we precisely realize a flip this way. And so using one surgery, we can realize one flips, and we can realize all the handle slides. And this way, we can simplify the decomposition of the manifold into a genuine trisection. Of course, when we do this one surgery, we attach additional handles to manifolds. So one has to be very careful here and make sure that at the end, these one handles can be cut back. But we show that this is all possible. And so this, where is it? Just a second. Right, so this kind of, and this shows that a manifold M admits a homology trisection by balls, if and only if M admits a trisection by balls. This basically shows that because the M is too big, as I said, whenever we have a decomposition of the manifold M into 3 smooth balls, we automatically get a homology trisection by balls. So this way we prove this theorem. And so this is all that I wanted to cover. So basically, I discussed this cut, I discussed B cut and B cut D. So this is all that I have for today.
Okay, thank you very much, Rustam. Are there any questions?
I have 2 questions. So the first is, at some point you wrote a conjecture, and it was comparing crit and crit with a dot.
Right.
And I forgot what crit was.
Crit was the minimal number of critical points of functions on a manifold. So crit M is something like more standard, so to say. So let me just write it. So crit M is a minimal number of critical points of a function. So F just arbitrary function. Right. And on the other hand, crit dot M is the same, but we consider F a function. So F a function with only cone-like singularities. And those cone-like singularities are singularities that are not infinitely degenerate.
I see. Okay, so in the first case, you just consider all functions. Okay, thanks. And,
Right.
and then I would have another question, which is about this last part. So what can you say, if you can say anything, of 4 manifolds which admits a filling with 4 bolts?
Right. So if a manifold is simply connected, then it definitely it's such a filling. But otherwise, so if the manifold M is not simply connected, then frankly we have not thought about this question. So I think that this could be a difficult question. So, of course, for a manifold being simply connected, it simplifies a lot. It makes a question much easier, and that is why we first considered this case.
Okay, thanks.
Sure.
Any other questions?
I have one question, Jesus. Rustam, have you computed, so for this conjecture that crit M is equal to crit dot M, have you computed many examples where you can actually find functions with only cone-like critical points that realize crit M?
Yeah, so here actually the problem is that like if you, so all boils down to fusing critical points. So you have some critical points that you want to fuse them. Because if, for example, if you start with a function that realizes this minimum, right? So then what you can do is you can just perturb this function and you have a Morse function with many critical points that kind of knows that you can fuse them back, these critical points. And so the question is that, okay, can you fuse these critical points back in a generic family? And so we thought about this, and kind of all the examples that we see are trivial, so to say. So all examples that we constructed, if we can fuse some critical points, then so what I mean is that, like, for example, if you have a function with critical points such that the descending disks do not, so that this, for example, critical points are on the same level, then we know that these critical points can be fused. But to find a complicated example where critical points can be fused is, it seems very complicated. We couldn't find any. We thought that maybe if we consider something like Mazur manifold, because over there all the abstractions are trivial, so we thought that maybe in that case we can fuse something. But in the case of Mazur manifold, it turns out that we cannot fuse anything. And so basically, what our intuition is that if something is obvious to fuse, then it can be fused. But if it's not obvious how to fuse critical points, then they cannot be fused. And then in these cases, kind of these two notions are just they're obviously the same. So that's why we think that they're the same. But we don't have any like decent arguments to showing that these two notions are the same.
Okay, thanks.
Yeah, but
Okay, well, I think there are no more questions. Thank you very much, Rustam, for your talk.
thank you. Thank you.
So I'm stopping now the recording. Chat.